So our last lecture was about the gas laws, and I would remind you again of the difference between law and theory. So those laws just say what's happening, not the why. Today I'm going to talk a little more about some of the why behind it, and then I titled the lecture as gas stoichiometry because we're going to get a little more into some other calculations other than just the standard gas laws that we use. So we have this set of gas laws, and we've been working on these for like literally hundreds of years, at least a couple hundred now, and watching behaviors and just saying, well, okay, what happens? And that's the law side of this. But now let's talk a little more about, well, why do we think it does work that way? Why, when you heat a gas up, does it expand? Why, when you put a given volume of gas under greater pressure, does it heat up? So there's several pieces of this. We're gonna think of gases in a bit of simplified way. We're going to talk about gases as being composed of the text. Your text says molecules, and I want to be a little more agnostic than that and say that gases are composed of gas particles, be they molecules or single atoms or whatevers, that are in continuous motion, that these particles travel in straight lines, and they only change direction, as with most masses that we talk about in Newtonian physics, when they're acted on by an outside force. But mostly the only things that can act on these gas particles are other gas particles or the walls of a container that they are contained in. So when they hit something, other gas molecules or the walls, that's when they can change their velocity vectors. So the molecules composing the gas, for this theory to work in its simplest form, we need to consider the molecules composing the gas to be what your text says negligibly, that's harder to say than I expected, negligibly smaller than the space that they're in. So, like if we have a liter of gas, an individual gas particle doesn't take up a reasonable part of that volume, that liter, at all. It's almost zero. I mean, it is approaching a limit, which is zero, if you want to say it in math terms. So the actual volume of the molecule, we need to be able to consider it to be essentially zero. And then we think that the pressure, the thing that we are measuring is pressure. Pascals is a unit that we're going to use for it mostly. Atmosphere is another unit we'll use for it. But that pressure that we can measure is a result of these small particles of gas slamming into the walls of the container. So another little bit, and this won't matter much to you until you get deeper into the chemistries, but we have to assume that the gas molecules do not exert other forces on each other, like magnetic or electrical forces, and that their collisions, if you had physics, are perfectly elastic collisions. That means that you don't lose any energy to non-conservative forces when the gas molecules collide. And then this one we're going to talk more about. This number 5, the average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. All right, now so watch my pointer here, and I'm going to try to demonstrate. I usually do this with my hands when I'm doing this live in class, so I'm going to try to do it with the laser pointer and see if this works. So what we're going to say is that a gas that is at high temperature is vibrating very fast, and so because this is vibrating very fast, it has a high kinetic energy. As we cool this gas down, it starts to vibrate less quickly. As we cool it down more, even less. And eventually reaching where we've cooled it down so far that it stops. And that's what we call absolute zero. And because it's where the gas stops vibrating, that's why Kelvin can't have a negative value. Because there's no such thing as going any less vibration, kinetic energy, than not vibrating. Negative vibration doesn't have any meaning here. So Amundsen's law is this idea that if you hold volume constant, I'm showing this with my graphic here by these being exactly the same volume. If you hold a volume constant, but you increase the heat, the temperature of a gas, it will cause an increased pressure. Okay? Now, I'm going to use it, and I'm going to go back to an analogy over and over again here. So up top, see this graphic here. I'm going to use an analogy of middle schoolers trapped in a room. Instead of actually boiling my middle schoolers, we're gonna apply energy in the form of Mountain Dew. So we have a certain amount of middle schoolers in this room. I promise you, if you apply more Mountain Dew, they will bounce off of the walls harder. And remember, according to the kinetic theory of molecules, we think that's what causes this thing that we read as pressure, how hard our middle schoolers or our gas molecules are hitting into the walls. If you try this experiment at home, I promise it will not be good for your drywall. You should not do it. Okay, similarly, Charles's law, it's kind of like Amundsen's, except that this time we don't constrain the volume. We let the volume change if it wants to. So if we have a given volume of gases and we apply kinetic energy, we apply a heat to that, right? Then what's going to happen? We're going to see it. It's going to expand. And to go to my middle schooler analogy, right? And let's say you've got nice, calm circle of middle schoolers sitting in the middle of the floor. But if you apply those Mountain Dews, like I was talking about, if you apply that energy source, that circle is going to start to expand until it gets totally out of control. It will grow. And so it's going to force the container, if the container doesn't constrain the volume, it will have to get bigger. So Boyle's law works a little differently, but it's still going to work with our molecular collision theory. So let's say if we have, in this first piece of the graphic here, we've got a certain number of molecules in a given volume. And we measure the temperature of that. Now, the temperature, we think, is based on how hard and how often the molecules are slamming into the container wall. Well, if we were to push the cylinder down so that we give the gas less volume over here on the right, and actually, there's the same number of molecules here, right? We've got 6 molecules in both cases, but the 6 molecules on the right are constrained to a smaller volume. So if we measure the temperature by measuring the edges of that cylinder, what's happening? Well, for any given area, the molecules are slamming into it more often. And so we are reading a higher kinetic energy from the average collisions hitting the walls there because we've constrained it to a smaller space. Middle schooler analogy is getting a little more difficult for me as we go here, but I guess if we measure our impacts of middle schoolers by like looking at the sheetrock after they've been there, if we put them in a very large room, these 4 middle schoolers here, put them in a very large room and check the sheetrock, maybe there'll be a little damage. But if you put these same 4 middle schoolers in a very small room together and come back and check it later, there's going to be a lot of damage to my drywall. Okay, now this one's a little easier. So for a given pressure and temperature, Avogadro's law says if you put more molecules in there, they will exert more pressure. So similarly, we have our set of middle schoolers in a given volume here, right? They're gonna bang into the walls. They're gonna damage the walls to some extent anyway. But if you take the unfortunate step of stacking in a whole bunch more middle schoolers, there's gonna be lots more damage. Okay, similarly, and I should have drawn this graphic differently such that the volume was constrained. But if you shove more gas molecules in to a given situation, it is going to result in a greater energy overall. Now, this one might be kind of new to you, and so I'm going to call it Dalton's law here, and I also see it referred to as the law of partial pressure sometimes. I've written out the mathematical form up here that total pressure is equal to the sum of the individual pressures. All that means is, let's look over here at the graphic. So here we have, on this left side, we've got a cylinder of a given size that has a certain number of these purple molecules in it. Well, from what we've been doing before, we know that there is a measurable pressure and temperature related to that given volume and number of moles of particles. So there is a pressure that results from this number of particles in there. But then these are a different kind of gas. The red ones, they're still going to act like an ideal gas. They're just a different identity of gas. Behavior is the same. And they also exert a pressure off of this. So we're going to say that's P1 from the purple, P2 from the red. What if in that given volume you shoved all the purple molecules and all the red molecules in the same volume, like this graphic up here? So what this law says is that the total pressure that we would read here is equal to the pressure that would be exerted by the purple molecules alone, plus the total pressure that would be represented by the red molecules alone. So it's just an additive function. You could have two types of gas molecules, 3, 700. It doesn't matter. Dalton's law just says that you can sum up the individual partial pressures, that's what we call them, to get the total pressure. And a lot of times in working problems on this, we're going to go the other way, and you're going to know something like that the total pressure, okay, so the total pressure that you're sitting at right now is probably about 1 atmosphere of pressure. And some fraction of that, let's say 0.23 atmospheres, is the pressure caused by oxygen, right? And 0.77 atmospheres is caused by nitrogen. So those two different gases apply a pressure differently, but the total pressure, 1 atmosphere that you feel, is just the sum of them. All right, and now for a little bit of stats. However, this is not your normal stats. I hope somebody can catch my joke there. This is not a normal stats that you're used to. We're going to talk about something called a Boltzmann distribution. And it is a different shape than a Gaussian or normal distribution. What you usually deal with in stats is you talk about a normal distribution, and basically the sides of the curve are symmetrical, right? So if you find the mean value, if it's a truly normal distribution, then everything to the right of that occupies the same area as everything to the left of that. So the half integral is the same. But in the case of a Boltzmann distribution, that's not the case. So we're going to look at it this way and talk about how this works. We're going to go to the next slide to talk some more about how temperatures work. But on this slide, I wanted to point out a couple of things. So in stats, we use the mu symbol. It's the Greek. It's a Greek M, but it looks more like a U. So this is the percentage, the middle percentage, but then this is going to be another mean that we're going to talk about over here. It's going to be a type called RMS, and it stands for root mean squared. Get to that in just a second here. All right, so let's see. So let's talk these things through. So it looks like I've already put a little bit of my graphic on here. Some more of this will catch up in a second. So let's consider this is for nitrogen right here. So nitrogen gas. So each particle consists of 2 nitrogen atoms bonded together, and that's their molar mass, 28.02 grams per mole. So if we look at gas at 100 degrees Kelvin, then it has this first distribution here. That almost looks like normal, except for you see this tail part down here. It doesn't have a reflection on this back side because this is graphing molecular speed down here, and so we can't get below the 0 as we're kind of chopped off. Okay, but this tail on the upper end is going to become important in a minute. We're going to talk this through. All right, now let's consider our, so that is at 100 K. But now let's consider our gas at a higher temperature, let's say at 300 K. So we're significantly warmer, and our distribution starts to spread out. But here's what we're going to say with this, that it's still a distribution. There are still a few molecules that have really close to 0 kinetic energy or molecular speed on this graph, but it works the same. And there are a few that have a lot of kinetic energy. But look at what's happening to the middle of our peak. It's starting to shift upwards, right? Starting to shift to the right to higher energies, but our shape is not maintaining the same because we're stretching out even further to those few percent that are really high energy. And if we go even further to, let's say, 700 K, that's really warm. And in that case, you start to stretch out even further. So even though our peak is still right here, we've got some few molecules out here that have an extremely, extremely high kinetic energy. You can look at it the same way with, so look how similar these graphs are. But this time, I'm not graphing nitrogen at different temperatures. I am graphing everything at 300 K. But now we've got, so everything's at 300 K, but this is helium, so it is a very small density, right? So you've got 4 grams per mole for helium versus here's our 28 grams per mole for nitrogen, just like the 300K was up there. Or a much heavier molecule with 71 grams per mole for chlorine gas. Well, look at their distributions. Those speed distributions for the chlorine look like the nitrogen at a lower temperature, and the distribution of the speeds for the helium molecules look like the nitrogen at a much higher temperature. And that's because this is really a graph of kinetic energy and not just speed. So we find a value called mean, mu RMS, or we call it root mean squared value, right? And so this is how you calculate it. And this symbol right here, your textbook uses as molar mass. We're going to use that again in a few minutes. But you wouldn't do this calculation by hand, by the way, so don't expect to have to do that on an exam, because it's not the type of calculation you would do that way. You just need to know that this distribution matters. And y'all remind me to talk some more about it in the classroom, and I'll give you some applications of it with talking about things boiling when you wouldn't expect them to. All right, so shifting a little bit to some of the applications of this theory and what we think it does, gives us some ability to look at a few new things in the way they work. So one of them is diffusion. And I am mixing the terms diffusion and dispersion carelessly here, but I don't think it matters for where y'all are. Just know that later on, those two terms could start to take on a slightly different meaning, especially if you're doing some high-level engineering or physics work, or in my case, some geology work. But anyway, for now, they're going to mean the same thing as far as we're concerned. Just from where there's a high concentration of stuff to where there's a low concentration of stuff, that gives us a direction that gas molecules tend to move. And so we can talk about their rate and how it is proportional to the concentration difference, the gradient. Well, here's how it works. So remember, we think these molecules are just like jetting around until they slam into some other gas molecule. This corner shown in the path here, that's us slamming into some other gas molecule. And it causes it to bounce and go a different, oh, it hit something else. Oh, it hit something, and it just is bouncing around. And you see how these paths can kind of take it anywhere in let's say, a room. Well, that becomes important because it might be hard to read what's on this 5-liter bottle here, but that says hydrochloric acid. Well, if you open a reagent bottle of hydrochloric acid and stand anywhere close to it, your nose hairs are going to start to burn because you can probably see the fumes coming off of this. And that's because all those individual molecules, remember, some few of them, according to that distribution, have a very high energy and they can go a lot of places. Well, they're going a lot of places right here. See that? That's called diffusion. And we will calculate with this in class. This is a slightly different term, so make sure you hear that. This is probably horrible with my accent and trying to hear it, but diffusion was the last slide. This slide is effusion. I probably won't enunciate it quite so well most of the time, but effusion is a fairly corner case of defined as escape from a pressurized vessel through a pinhole to vacuum. And it turns out that the rate is proportional to the inverse of the square root of the molar mass of the compound. So here's how, and we'll work this in class, and it'll make more sense when we start to actually plug numbers in and play with this. But proportionality symbol here, 1 over root molar mass. And I wanted to walk through some algebra shenanigans with you. Now, so different textbooks go to different extents on this, but a lot of you are science majors, and you'll probably have physics classes, you'll have upper level science classes in other places, and eventually you'll be reading some scientific literature and other stuff like that. And one of the important things to know is a lot of authors will say things like, well, the math should be easy for the reader to work out. And what it really means is we don't want to work this out for you. So I don't want to do that to you. So I want y'all asking me anytime that you want me to work through the math. How did they derive that? And I want to help you get there. But here's an example of. So given, we got some givens up here. Given that we're going to talk about what this is, PV equals nRT. We mentioned it in a previous one. It's the ideal gas formula from last lecture. So we know that pressure times volume is equal to the number of moles of gas times that ideal gas constant times the temperature, in Kelvin, of course. Well, you also know that density is defined as mass over volume. So the amount of mass something has divided by the volume it takes up is the definition of density. So you can use that. So I'm going to divide both sides of my ideal gas law by P. It's going to be V equals nRT over P, right? Well, let's see. I've rearranged over here on the right my D equals M over V as, so I've multiplied by V divided by D. So now V equals mass divided by density. All right, cool. Oh, but I can substitute that because look, This equals here says, well, if there's a V, that's the same thing as an M over D. So I'm shoving that in to the equation there. So now I have M over D is equal to nRT over P. Multiply both sides, and I'm now at, okay, so I'm multiplying by D over N. One of those is coming from each side here, right? So basically multiplying by D, dividing by N, both sides, okay? So now what have I got? I've got the mass of gas divided by the number of moles is equal to the density times the ideal gas constant times the temperature divided by the pressure. But you know what? We know that molar mass is a quantity that is defined as the mass that we have divided by the number of moles. Now, usually we talk about molar mass as being, like we did in one of the practices, we found that calcium hydroxide had a molar mass of 70 grams per mole. That means 70 grams for every 1 mole. But you know what? It would also be true to say 140 grams for every 2 moles. You could do, or 210 grams for every 3 moles. So that works. So it's just the total mass divided by the total number of moles. And if y'all hear some dogs growling in the background, nothing bad is happening. That's puppies playing. So I'm going to take, now that's our definition of molar mass. But it's just anywhere there's an M over N, that's the same as saying mole. Oh, wait, there's my M over N. So I could substitute molar mass right there. So molar mass is the density of gas times the gas constant times temperature divided by the pressure. Multiply both sides by the inverse again, right? So what do I have? The molar mass times the exerted pressure divided by the gas constant times temperature gives me a density value. Density is a measurable thing. So this gives us an ability to find something we could actually measure in a lab to try to sneak up on things like molar mass. And if you've ever asked yourself, I wonder how do they get some of these values? Like helium has a molar mass of 4.003 grams per mole. Well, this is the how. We sneak up on it by rearranging the algebra so that we can get it to something that we can measure in a lab. Well, okay, well, what does that do for us, though? Well, it gives us some more relationships, too, that we can start to graph or to look at the proportionality of. So we can say that a higher molar mass should yield a denser gas. This becomes important if you ever have situation, we had a situation over in Birmingham where some chlorine gas was released. Oh no, a plant has released chlorine gas. Do you go uphill or downhill from that gas? Go uphill. If it's chlorine gas, definitely go uphill because chlorine is denser than nitrogen gas, which is most of air. So it's going to be a higher density than the nitrogen gas, the air. So it's going to sink. Don't go down in the valley because that's where the gas is going. You could look at this idea. If you have a higher pressure, it is going to lead to a higher density. Or if you have a higher temperature, it is going to lead to a lower density. And that's because of where the maths are. The pressure is up top in the numerator here, so it's proportional to density. But the temperature is in the denominator, so 1 over temperature is proportional to the density. Another tidbit, now this one doesn't come from the density side. It just comes straight from the ideal gas law. We can rearrange this. Look, I'm solving for V here. Just go divided by P. Okay, but you know what we know? We have some standard conditions. So if you consider 1 mole of an ideal gas, so where's my 1 going to go? It's going to go in here for my N, right? So 1 mole. And let's see, the R, now the ideal gas constant, well, that's constant everywhere in the universe. And standard temperature, we could say 0C, a lot of gas work is done at 0C or 273.15 K. And we could define our standard pressure as what you're feeling right now at about 1 atmosphere. There's my gas constant. Just remember, these gas constants are the same. You just have to make sure that your units match up. And since I'm doing this in atmospheres, I want the one with atmospheres and moles and K. And we're going to get a result in liters. So when you crunch these numbers, you get at 0C, 1 mole of ideal gas at 0C and 1 atmosphere represents 22.4 liters. So if you think of a really, really huge balloon, 22.4 liter balloon, that represents a mole of gas. Now, of course, that's at standard temperature of 0C. Probably what matters more to us is what if we had that at like room temperature gas instead of quote standard temperature. So room temperature, we would just, instead of 273.15, we would just do it at like 20C. And I'm sorry, I did this at 25C. You could do it at whatever to get a volume. But look, fairly close, but 24.5 liters. So at 25C and 1 atmosphere, a volume of 25 liters, that's how much a mole is. That's a mole of gas molecules. And so in class, we'll run through some of these calculations where we're finding the total pressure or one of the partial pressures or something. For instance, we could find like the partial pressure of CO2 or N2 in air or something like that, because it just adds up. So you probably, I hope, saw in Chem 1 the idea of using mole fraction as a measure of concentration. And that's just saying like if there are 25 moles of one gas and 75 moles of another gas in a given container, well, it's 25% by count or by mole fraction of the first gas, because there's 25 out of a total 25 plus 75, 100 moles, right? So that's what mole fraction means. So you can do the fraction of gas, right, should give you the partial pressure if you know the total pressure. We can walk through this in class. I think that'll make more sense calculating these. But basically, their total pressures add up. Well, then, if we solve for pressure here with our ideal gas law, right, and then if RT and V are the same in both cases, well, it must just be that NA and NB are different. And it does work that way, that the mole fraction is equal to the number of moles of one divided by the total moles. You could just take that fraction and multiply the total pressure to get any partial pressure that you wanted. And here it is stated in a mathematical axiom form that any partial pressure is equal to the mole fraction times the total pressure. So one thing that actually gets easier with stoichiometry of gases is trying to do, we did an example of a stoichiometry problem that you should have recognized from 1211, but stoichiometry where we have to take like a molar value and turn it into moles, or a mass value in grams and turn it into moles, or a whatever units we have, we got to get it to moles before we can do the stoichiometry and do moles to moles to do, for instance, a theoretical yield calculation or a limiting reaction calculation, but we always have to get moles to moles. Now I'm going to break that rule and I'm going to say, you know what? For gases, you don't have to. As long as they act like ideal gases, because they're proportional to, because you can say that the pressures or the volumes are proportional to the moles, then you don't actually have to convert to the moles. You can just do it in volume units. For instance, 1 liter of nitrogen gas plus 3 liters of hydrogen gas will yield 2 liters of ammonia. You don't have to do all the converting in this case to get to molar because it's a 1-to-1 proportionality. So you can actually take a shortcut here. It's one of the few places that it actually gets easier. So you could do a calculation here. You have 3 liters of each reactant. So I got 3 liters of this and I got 3 liters of this. Oh, wait, look, I'm going to run out here of my hydrogen gas first. Oh, that's already, I know what my limiting reactant is. So this is an easy calculation without having to go to moles at all. I've got 3 liters of each reactant. Hydrogen's my limiting. I get 2 moles of ammonia. All right, well, I succeeded in keeping this a little shorter than last time, but I'm working on that, y'all. I'm trying to get them shorter and shorter. Next time, we'll talk about condensed phases, more commonly thought of as liquid and solids. So that'll be the next video lecture, and you'll read sections 10.1 and 10.2 for that class. And I will see you in class to work some of these problems.